So I'll be presenting two short case studies on the use of high-resolution site characterization techniques applied at chlorinated solvent or DNAPL type sites. And for this one, I've chosen two sites, the Hamilton-LaBrae PCE solvent site in Washington, EPA Region 10, and the Bountiful Woods Cross TCE site located in Utah here in Region 8. And I think in both cases, these sites show an evolution of the use of the high-resolution site characterization techniques, particularly in the later stages as we look at ways to compartmentalize our site, shrink the footprints of our remediation technologies, and really hone in on where the mass is and where we need to treat with aggressive technologies and where we can hone our more passive techniques on areas of the plume as well. Now, before we jump into the case studies, I thought it was worthwhile to recall one of the slides I showed in the intro, which is some work that was done by a gentleman by the name of Martin Gerbeau in 2005, looking at very high-resolution vertical sampling at a PCE solvent site in New Hampshire in the U.S. And the findings were quite similar to findings I think that we've had similar experiences at other sites, but basically a lot of the mass, the majority of the mass, moving through a very small cross-sectional area of the site. And that is similar to experiences, for example, that we've seen for research in mass flux, the University of Waterloo, narrow plume cores that I showed in the intro. Many of those things play out here when we look at these PCE, in this case a PCE plume at high resolution. We see that something like 75, 80, even 90% of the mass discharge is occurring across a very small cross-sectional area of the site, which leads us to an opportunity for high-resolution site characterization and optimizing our remedies, improving how we apply those remedies, and really targeting them in specific zones and geologies where it makes sense. For instance, pump and treat has been shown to work quite well in places where we know a lot of the mass is moving in transmissive zones, and if we can target those transmissive zones with the right screen intervals, pump and treat can be effective at has been shown to be effective at some sites. At the same time, we know that our in situ remedies are going to continue to rise, and those require, quote, contact, meaning that we need to get our amendments or things that we're trying to help us stimulate the in situ technologies, whether they're biological or other amendments, oxidants and things of that nature. Typically they require a contact between the biological medium or the oxidant with the actual contaminant itself, and that can be quite challenging where we have zones of low permeability but very high concentrations, for example. So here is the Hamilton-LaBrae site. Again, it's in Region 10. So here's Seattle, Washington. And follow down the corridor of the I-5 below Olympia, Washington. Down here in the Chehalis, Washington area, there is a site called the Hamilton-LaBrae site, and that is literally the meeting of Hamilton and LaBrae roads. They happen to be right along the I-5 corridor, and there is what is suspected to be a midnight dumping at some point in the history. It is suspected that somebody came along and dumped a large quantity of PCE in Berwick Creek, which runs right along here along the highway and then turns left here and goes along Hamilton Road or LaBrae Road, following the contours. So this is a PCE dumping, and a site that had had about 10 to 15 years worth of RI activities prior to us coming in 2014 with a high resolution site characterization effort. Here's a depiction of what the historical groundwater or upper aquifer data from the upper aquifer, historical groundwater data from both the, quote, shallow zone and the deeper zones. And you can see here contours for the PCE contaminants. But again, it focuses on an area along the creek where it appears something, the PCE was dumped, and then that follows sort of the groundwater movements. But this is sort of the density, or at least some of the depictions of what we had, our understanding of the contaminant distribution prior to undertaking the high resolution site characterization effort, which took place in late 2014. Fast forward to 2014 now, where we came in with a series of tools, and I'll show a couple of visualizations of that. But essentially, we used the membrane interface probe and the HPT stacked with the HPT, the hydraulic profiling tool. So we have MIP and HPT response. HPT telling us something about the geology, and the MIP response telling us something about the distribution and strength of the signal for the PCE contamination. And the idea was that we wanted a rapid evolution of the conceptual site model at this site that had been undergoing many years worth of characterization activities. The idea was, can we come in, evolve the conceptual site model in near real time, and then and then take that information to help us design an effective remedy. So in 2014, the team came in, and it works sort of like you see here in the center. We collected all of the direct sensing data. That information was uploaded to a team site, the Scribe database, where a visualization contractor was able to collect that information. They were on the east coast of the United States, the site's on the west coast, and by the time we were at the site the next day, we had a visualization created for the work that had been done previously. So really a real-time evolution of the conceptual site model as it was happening in the field. And one thing that does is it helps us to focus on data interpretation, not just presentation. So we really are, as a team, as the information's coming in the field, looking at it and trying to make decisions about do we have enough information to move forward with some of the remedy design applications. And that includes all of the site decision makers, so the state, EPA, and others, all involved in looking at that data and making decisions. And that can really compress the time frame where we're looking at trying to get consensus on what the data means, and it also helps us with cutting out repeat mobilizations and things of that nature, and focuses on the root causes and not the symptoms of the problem. In other words, focusing on the high mass footprint, which ultimately is the problem for the remaining groundwater plume, which they've been monitoring for a number of years, and really pushing that decisions process forward and compressing it from multi-years of investigation to just a short time frame to try to make decisions on remedies. Okay, so here we have the Hamilton-LaBrea site, and this is the membrane interface probe and hydraulic profiling tool work that was done in late 2014, resulting in a rapid evolution of the conceptual site model and leading to a design for a thermal treatment and enhanced reductive dechlorination. So using those two technologies together. So here we are looking at the site. Here's the I-5 corridor, Berwick Creek, which runs just along the highway here, and you're looking at interpolated MIP response here from the halogen specific detector, or XSD, and you see you're looking at interpolated MIP response for the halogen specific detector above 100,000 microvolts, and also an interpolation of the hydraulic profiling tool and the lithology from that. And so the red areas, for example, is where your HPT pressures are very high. You're moving into much tighter material, and we're using that to help us interpret these important geologic features, the glacial till in brown and the outwash there in blue. And the nice thing is we can actually, first of all, take a look at the MIP pushes. Now there's a 3-to-1 vertical exaggeration on this visualization, but these are 45-degree MIP pushes that were actually placed under and beneath Berwick Creek. And then we can look at the interpolation of the MIP and the HPT to look at the relationship between where all of that MIP response and mass seems to be, that PCE mass, and also the important relationship of where those reside in relationship to the till and the outwash material. And we can actually march right down the creek in this case, looking at the MIP response and geology. A series of slices. Now we also have with the MIP the ECD, the electron capture detector. So here we've now showing the ECD response. It's typically has less sensitivity and linearity than the XSD, the halogen specific detector, but we like to show the responses from both. And here we have just the MIP ECD response, everything above 5,000 microvolts from the MIP, and again the interpolated geology from the HPT. And again, we can march right down that creek and look at the relationship between those MIP responses, where the creek is, and where the majority of that, in this case, MIP ECD response is, which will help us map out the more dissolved phase plume, and also that NAPL and area that we plan on targeting here in this zone for the thermal remedy. But remember, there's also an enhanced reductive dechlorination component, and we want to be able to target those zones moving down gradient. We want to take advantage of the heat that will be produced from the thermal design that goes in this area, take advantage of that residual heat that will help us with dissolution and reductive dechlorination as we move through this zone where we have the planned injections for enhanced reductive dechlorination. So here we're looking at historical soil data above 10 part per million, which is an important threshold because essentially we are designing around the 10 part per million and chasing that 10 part per million threshold with the thermal treatment technology. And then out here in the lower 4 ppm type contours, they're interested in doing enhanced reductive dechlorination and taking advantage of the residual heat from the thermal system. But here's what the data looked like prior to the 2014 high resolution site characterization effort. Now we go ahead and add some of that, and you can see how much richer and significantly improved the data set becomes. With all of that, we have the interpretation, of course, of the lithology from some of the logs, and we're not showing any of the MIP data here. This is all just multi-level soil sampling and grabs, and again, you can see right here through the high concentration source zone. This is going to be our thermal treatment area through here. And we can, like the other depictions, look at and march right down the creek looking at the relationship of the geology to the distribution of the higher concentrations of PCE, what our soil sampling locations and multi-level soil samples look like. All of those things we can do with a much higher data density set. And one thing I should mention too that I didn't mention with the MIP data set was that I think it was day 2 or 3 of the high resolution site characterization effort. You see a couple zones right here with the targeted in red. Those were actually identified on day 2 or 3 of the MIP effort and came back in with the sonic drilling technology and actually found DNAPL at those locations. Now this is a site where they had been doing RI type activities, sampling and investigation for more than 15 years, and no one had ever identified DNAPL. We were able to find it, locate it within 2 or 3 days of the MIP effort, and then really go back in and delineate what those soil concentrations look like to help us design what you'll see later as a thermal remedy through this area, and also understanding that there are some higher hydraulic conductivity pathways, some higher soil, potential soil sorption going on here with higher concentrations of PCE. And when we look at the groundwater data too, you'll see that some of the transmissive zones and some of the plume moving out in this direction. So the thermal will be in here right under Berwick Creek, and then they'll be doing enhanced reductive dechlorination out here in various areas of the plume to try to help attack that and using a combined remedy. And then finally at Hamilton-LaBrae, let's look at the historic information based on, this is looking at PCE above 4 parts per million, 4,000 micrograms per liter, based on historical information. And you can see it's relatively low density, and of course the interpolators do things like putting plumes where we really don't have a lot of information. But as we add on the high resolution information from the 2014 event, you see that the 4 ppm plume contour becomes much clearer, and that is really going to help as we move towards not only focusing here in the source zone for thermal, but understanding some of the higher concentration and higher hydraulic conductivity transport pathways out in this zone, and over here on this side of the site looking to do injections and placement of a barrier for enhanced reductive dechlorination, taking advantage of that residual heat from the thermal system, which will be placed in this area. But we can do the same thing with the historic information, but you can see with all of this information, it is significant. We have significant groundwater data now that we are able to look at, multi-level data, MIP response, XSD, and other things that have helped us interpret the geology. And we now have a much finer understanding that can lead us to ultimately an improved remedy design that really helps us target our big hammers, our expensive technologies like thermal, and helps us take advantage of residual heat and with some of our more passive techniques like enhanced reductive dechlorination. So although the high-resolution site characterization effort was completed in 2014, the reality is that when you're trying to apply, for instance, an aggressive thermal remedy here on Berwick Creek, which happens to be considered salmon habitat, and it's wedged in between a major U.S. highway, obviously there can be challenges with trying to apply remedies. So in 2020, actually remedy construction has begun. And essentially they have a thermal footprint for where the thermal heating electrodes will be placed. And they had to reroute Berwick Creek and then reline it with a high density polyethylene liner and a series of other things, which I'll show in a moment, to keep the creek and the salmon habitat available in the space while actually heating the subsurface, but not boiling the stream or the salmon habitat. Quite an interesting application. So it looks something like the design here, where we had to excavate the creek, place a high density polyethylene liner in, a smaller area for low flow conditions where fish can still travel up the creek, and we'll show you some pictures of that here in a second. And this is what sort of, I think it was about 120 or 30 electrodes or so, but this is the footprint of the thermal design from the thermal contractor TerraTherm. It's just a draft of what the thermal design looked like, but shows all the placement of the electrodes and Berwick Creek and some of the challenges with some of the infrastructure that they have there. So as I said, construction of the thermal remedy portion began in 2020. And what's interesting, as I mentioned, is we have the challenge of trying to reroute a creek with very limited space, a major U.S. highway on one side, and a stream that is considered critical salmon habitat in the state. And so we have to apply a thermal remedy almost directly under that stream. And how they're able to do it, as we see here, is the excavation taking place on the left. And we can see that there is indeed a native soil silt cap. And then on top of that, you can see the native soil silt cap here. They placed a layer of gravel, which can be seen here. And then there's an insulating foam. Remember, we're heating the subsurface directly below this, and we don't want contact with that heat to the stream bed, which could impact stream temperatures for the salmon habitat. So there's an insulating layer here, an insulating foam layer, and then on top of that, the quote mega ditch, the larger HDPE liner that you see here, and then within that there is a smaller quote half pipe that allows fish passage through that zone during low flow conditions. So really paying attention to the critical salmon habitat while still being able to apply a pretty aggressive thermal remedy directly under the stream. And then finally, just a few photos courtesy of Tom Cady with ERT, who has also been involved with this site heavily over the years and the application of the high resolution site characterization. But we can see here the thermal infrastructure going in now along Berwick Creek. Eventually there will be, or there is a cement cap that goes over that. But essentially the creek is now in place. We have the bypass going in the creek flow, and you can see all of the thermal electrodes being placed in the infrastructure for the treatment of that whole system. And so this is going on now. We're very excited about the prospects for this remedy doing a pretty bang up job quickly. and really getting that site, moving that site quickly to closure. So stay tuned. So here we have the Bountiful Woods Cross Superfund site. We'll be presenting a short case study for a chlorinated solvent site. So for the Bountiful Woods Cross site, I'd like to start with some acknowledgments. Our remedial project manager, Sam Garcia, Ian Bowen, our senior hydrogeologist, was instrumental in helping me pull together some of this material. Tactical remediation, I'll show some of their figures. Michael Stork with Utah Department of Environmental Quality, and a number of folks with our RAC contractor, CDM Smith. Nathan Smith, Neil Smith, were provided a number of pieces of material, and Thomas Cook and his work on some of the visualization, and a number of other folks who have helped out on various aspects of that project. So I want to start there by just acknowledging the great work of all of these folks and thanking them too for helping me pull together some of the materials for this presentation. So a quick history on the Bountiful Woods Cross site. It's located in the great state of Utah, just north of Salt Lake. So here we have the northern sections of Salt Lake City and the town of Bountiful, Utah, and our site located here in the center of the valley with the purple mark around it. You have mountains just to the east, and then extending to the west out in this direction, the Great Salt Lake. The site itself was identified following the CERCLA process, identified in 1987, had preliminary assessment and site investigation activities take place from 1995 to 1998. By 2000, it was placed on EPA's Superfund National Priorities list with a series of remedial investigation and feasibility activities taking place through the 2000s. Now we're focusing on OU1, Operable Unit 1, in this area where the groundwater, where the remedial action began in the 2007 timeframe. Why Operable Unit 1? Well, it was a specialized carrier of bulk petroleum, asphalt, and solvents. And of course, it is really just a parking lot that you see there today, but that historical facility was used to service, clean, and park things like tractor trailers and tank trucks. And of course, the TCE, trichloroethene, was a primary parts cleaning solvent used, and therefore the primary contaminant released at the site. So we have a lot of TCE and its degradation products, cis DCE, vinyl chloride, and ethene. And the concentrate, the contamination itself, generally about 100 feet or shallower. So deeper portions of the OU1 plume right at around 100 feet deep. But shallower portions of the plume on the order of 50 feet deep. The site itself is in the remedial action phase using enhanced bioremediation or enhanced reductive dechlorination, where they're using a series of biobarriers and injection wells to place emulsified vegetable oil and lactate to stimulate reductive dechlorination. Now the site has some challenges that remain. Overall, the remedy's been very successful at removing concentrations of TCE and breakdown products in the aquifer, but there are some challenges in the middle portion of the plume and the source zone where there seems to be issues with matrix diffusion and finding higher mass located in low permeability units, creating a potential back diffusion and diffusion rate limited dissolution of that material coming back into the transport zones. And there's actually quite a history of sampling and remedial activities at the Bountiful OU1 site. In particular, I think we should pay attention to some of the applications of the high-resolution site characterization efforts, but you can see early on using triad activities to place biobarriers and injection sites for some of the bioaugmentation. They use passive diffusion bags and well sampling. Later in the 2014 timeframe, there was a large membrane interface probe investigation, which helped placement of the biobarriers, biobarrier 1, 2, and 3, and also some down gradient investigations using the hydraulic profiling tool and the groundwater sampling from that in 2014. And of course, there's been a number of activities more recently at the site looking at activities in 2017 where they did some post-enhancement permeability enhancement of small units of low permeability that seem to be carrying a lot of mass, and we have some results in the case study that show that. And again, the membrane interface probe and MIHPT, membrane interface probe and hydraulic profiling tool, again used in 2019 to help with some of those down gradient hotspot fracturing events that I'll talk about. So look at the groundwater at Bountiful OU1. We have the source area located down here in the lower right-hand corner. And of course, this is the shallow groundwater. So we've got about a mile-long plume here going in this direction of TCE and breakdown products, and a number of biobarriers which were placed along the axis of the plume, and injection points where they've been actively remediating. Here's a look at the deeper in the right-hand side here, the deeper groundwater contours. Again, shallow contours, not steep gradients, but essentially moving to the west, northwest, away from the site, away from the source area, past the refinery here and out into this area is the toe of the plume. Now the site, in terms of depth to water, when I show the shallow contours, most of the wells that we talk about that are in the quote shallow portion of the aquifer are screened on the order of 20, 30, 40 feet deep. The stuff that shown here as the deeper well screens, many of them are screened in the 50 to 75 range, with several leading up to more than 100, about 100 feet deep. So shallower portions here, deeper portions, but the groundwater gradient and direction are pretty similar, shallow and deep portions at the site. As I mentioned, the TCE plume there in the Bountiful OU1 is being addressed with in situ bioremediation, which is essentially a series of treatment zones. So again, our source zone down here in the lower right-hand corner of Figure 14. This is the parking lot where you'll see a number of the wells that are right in the source area, like HMW17D, HMW 101, and others, 102. And then we follow the plume along in this direction. And you can actually see, in this case, we've got the biobarriers mapped out as well. And those are located here. So we have the source area, just down gradient of that source area is biobarrier number 1, which again, these are injected biobarriers that are driving reductive dechlorination. Biobarrier 2, located in this zone, has 2 components, one here, one located here. And biobarrier 3, further down gradient, also has 2 components, a biobarrier in this zone and another one just on the other side of the railroad tracks. And that technique and those biobarriers have been very effective at treating down gradient and keeping down gradient concentrations low, particularly of the main contaminant of TCE, but also of the breakdown products that are commonly associated with the reductive dechlorination process, which includes the cis-1,1-DCE and vinyl chloride, and ultimately, if we can get to ethene. But there continues to be a persistent source right here in the source area, and actually some high-resolution site characterization data has shown a couple of zones further down gradient that also have been targeted for some in situ fracking and placement of iron, an iron slurry to further stimulate that reductive dechlorination. So as I mentioned, the remedial strategy in OU1 being in situ bioremediation, trying to stimulate that or enhance that reductive dechlorination by injecting emulsified oil or lactate and I think they've done both at the site. But you can see here in the source area, the remedy work began in 2009. So down here in the source area, the installation of BioBarrier 1 and some of the injections and the well grid for those injections started in 2009. 2011, moving down to BioBarriers 2 and 3. And ultimately, the source treatment has been quite effective at reducing the flux. In fact, by 2012, the majority of the site had a 200 total chlorinated ethenes below 200 parts per billion. Unfortunately, we don't get to claim victory at that point. Ultimately, to complete a restoration remedy in Superfund, one needs to achieve the restoration goals, which in this case for the TCE are down in the 5 microgram per liter range, but also for all of the breakdown products, the DCE, the vinyl chloride as well. So we're getting close, but there are some areas within the middle of the plume that the site team has decided to go after a bit more aggressively. Here, just a depiction of what the source looks like today. Again, the historical buildings are gone. It's really just a parking lot, but there is a well-characterized and known source zone right in this area. As I mentioned, the majority of the dissolved phase plume, less than 200 parts per billion for total chlorinated ethenes. So moving in the right direction in the down gradient dissolved plume, but there still appears to be significant TCE mass, particularly right here in the source zone, as was identified and indicated by membrane interface probe and some of the high resolution work. And in fact, the team went and looked at, if we do nothing more in this zone and we assume first order decay, time to reach restoration goals would be in excess of 30 years. So EPA and state of Utah determined that they wanted to take a more aggressive approach, but really needed to hone down the characterization to target what has become a fracturing and emplacement of ZVI, zero valent iron technique, which I'll be showing in a minute. So I mentioned the source zone and of course the 2014 MIP work and some of the follow-up work, but essentially these are some of the depictions from some of the visualization work where we're starting to look at the distribution of the highest MIP responses that you see here in red, and also some of the lithologies which can be teased out of the electrical conductivity response, in this case from the MIP itself. So in this case, we're looking at essentially looking through the site to the northeast, and in that view, they were able to really hone in on those highest MIP responses and then use that electrical conductivity response to help map out some of the lithology associated with it. And in fact, you can see it is associated with some finer grain units in this area. So starting to use the visualization tools and the higher resolution MIP concentrations to really hone in on defining a box within this area that makes sense to try to go after with aggressive treatment technologies. As I mentioned, the team was able to use MIP and some of the high-resolution site characterization tools, particularly in the source area, and then using that highest MIP response and the lithology from the electrical conductivity response to map that out. And preliminary information suggests that the source mass, or this oddly shaped mass here, is really on the order of only about 400 square feet. I think when I looked at it, they were on the order of maybe 600 or more cubic feet, but a relatively small area where most of the MIP response, the highest MIP response, was coming from. In fact, there appears to be a fair amount of matrix diffusion coming from this high concentration zone that is in a low permeability unit. So they went ahead and used additional direct push technologies and sampling to really delineate that and come back in this case, and use the leapfrog visualization tool, which I'll show in a moment, to get an understanding of the MIP response, the high concentration zones, and the lithology associated with that. But suffice to say that most of the chlorinated aromatic hydrocarbon mass was found to be present in those low-K units, low-K layers, excuse me, interbedded silty sands found at 30 to 70 feet, and in particular, some of the deeper limits of it in the 60 to 75 foot range. So a pretty small area with a lot of high concentration mass and low permeability of that. So here we have a visualization of the bountiful OU1 source area. You can see HMW17D and some of the familiar names of some of the wells in the source area. And this visualization is depicting a lot of the membrane interface probe data from 2014, and it's using the Leapfrog visualization platform. And I'd like to thank Thomas Cook, who develops a lot of these visualizations for CDM Smith, to assist with their interpretation of data and development of conceptual site models. So thanks to Thomas Cook. But here we have kind of the source area. We can zoom out a little bit and then begin to look at the subsurface. And I've left on a number of the MIP points, MIP response points. And you can see that some information, a great deal of information is provided here. Each MIP response has a color coding, so where you find these big red responses, those are going to be your maxed out electron capture detector at about 88 million microvolts, so your highest MIP responses in this area. But you also get the electrical conductivity response, and you can see these big kickouts from individual boring logs, and those kickouts can then can help us interpret or interpolate some of the geology. So let's go ahead and turn on a couple of the key geologic points now and look at the interpolation of those. So we can turn on the clay, and there's not a whole lot of clay at the site. Really the unit that tends to be driving most of the location of the contaminant mass seems to be the low permeability clay units located here. So now we've turned on, and you can see a lot of those big kickouts here for the ECs are associated with these silty clay units. We can also look at gravel, so I can turn on gravel. These are going to be interpolated again from the EC response. It's not perfect. They can be a little bubbly. It's not reality, but it does help us interpret various zones where we think we might have mass storage, as we see here in the browns, in the clays, and the silty clays. And we can also look at areas of potential mass transport, like our gravels here and our gravelly sands. And I've dimmed those out a little bit so you can still kind of zoom in and see through various units to both MIP response and EC response and some of the interpolated units. So now we're starting to see the relationship between the high MIP response, nearby silty clays, and also transport areas of gravels in purple and silty sands in green. And then lastly, we can flood the domain if we show, the remainder of the material, which is the silty sand, and we show that in this case in yellow. And we can still, the nice thing is that we can still kind of zoom in and look at depictions of the bore logs, but also get a sense of the interpolated geology, all of that related to the source area. So again, here's our source area. There's the source mass that they estimated to be on the order of about 400 to 400 square feet or 600 cubic feet, something on that magnitude. And our plume heads off from the source area in this northwesterly direction, as depicted by many of that. So this is a way to, Leapfrog allows us to take advantage of, surface topography and maps and things that we can place into space. And we can also look at historical high-resolution site characterization data, in this case the MIP data. And one last thing we can even do is we can enhance our visualizations and pair them up with more elaborate modeling efforts. So in this case, just depicting a mod flow grid for a zone that's particularly important. And if I turn off some of the other units, we can really get a peek at what the mod flow grid looks like. And within the grid, you can do more sophisticated fate and transport modeling within various zones of this larger visualization. So understanding transport, for example, in this zone, but still understanding the relationship of various geologic units and also your highest MEP response, which tends to be your source mass. So a nice, helpful way to look at some existing data and really enhance our future high-resolution site characterization efforts and where they're going to go in and do some of the enhanced permeability as well. So the challenge at Bountiful OU1 in the source area has been and continues to be that high mass found in the low permeability units. So here we're looking at on the right just some historical data from HMW17D, the monitoring well very close to the source area that we just depicted with the 2014 MIP data. And indeed, over time, for instance, in 2008 and 2009, you can see higher, upwards of 200 micromoles per liter, in this case, of TCE, and also the production of the various breakdown products, DCE, vinyl chloride in purple, and even some ethenes. But the overall ethene production is relatively low, starting to see some enhancements in 14 and 15, but not a sustained downward trend for all of the contaminants and breakdown products. So the nice thing about the high resolution site characterization efforts in the source area was that given the understanding of the size of the area that would need to be addressed, that EPA and the state of Utah felt that they could support a more aggressive localized approach to go after that source mass right there near HMW17D, using the in situ biological or chemical treatment specified in the record of decision, but potentially enhancing that with some newer techniques. So, given all that new information, the size of the potential source area, and the availability of technologies, enter the new strategy that EPA, CDM Smith and the team, and Utah and the others on the team developed, using enhanced anaerobic bioremediation and recirculation, but also permeability enhancement, getting into those low permeability units and enhancing the permeability of those, and then ultimately taking advantage of those enhanced permeabilities and potentially using recirculated water to assist in further reductive dechlorination using the enhanced anaerobic bioremediation part of the strategy. So how do we do that? Well, essentially we're using a hydraulic fracturing technique. So in placing an amendment above, below, and within critical low permeability units, and the creation of that pathway, of course, allows for contact, which is critical in a quote contact sport like in situ remediation, where we really need to get our amendments and our contaminants together to really stimulate the processes that we're trying to enhance. And then the other component is biorecirculation, so extracting groundwater from down gradient wells, amending the groundwater with an electron donor, traditionally lactate or emulsified oils that they've used, and then re-injecting that in up gradient wells as a recirculation technique. And the thought behind that, of course, is that we can take what is estimated to be 20, 30 or more years to reach objectives in the source zone down to hopefully just a few short years, if everything goes correct with all of the remediation efforts. So how did the team actually plan to create that contact that's so necessary to improve the in situ remedies? Well, the idea is fracturing. So in this case, hydraulically fracturing the low permeability units with a slurry that then allows you to emplace zero valent iron in this case. I'm going to talk a little bit more about that process in a minute. But the depths for those fracture initiations, those targeted depths, of course, was all based on use of the membrane interface logs, the 3D visualization, some of the leapfrog work. I mentioned the numerical modeling domain that can be done within or outside of leapfrog, but used in conjunction with some of the visualization tools to even further enhance it. And of course, this is what a typical MIP response might look like in this case from the site, and we're looking at ECD response in yellow, so electron capture detector response in yellow, and this more orange color is the XSD, the halogen specific detector. So they had both working in some of the later MIP efforts where they were using multiple detectors. And in the blue here, this is actually the electrical conductivity response. And what's interesting is you indeed do see a number of zones where you have a high electrical conductivity response indicating a fining or a finer grain sequence material, and oftentimes our higher responses, in this case with the EC, and in this zone with both, we pegged out the electron capture detector, which is one of the limitations of it. You see you get a big response also from the XSD, which has a little more, a greater linearity, but that is also associated with a couple of higher EC zones here at between 35 and 40 feet, and the bottom of that right around 45 feet. So again, using all these individual logs, placing them together in 3D visualizations, and using that to develop a fracturing and zero valent iron emplacement strategy, which we'll show next. So what does the source zone permeability enhancement approach look like? Well, here we have a number of pictures, but essentially we are using a small skid-mounted fracturing unit shown here in the background, and all of those various amendments in the slurry can be delivered through a geoprobe platform. In this case, a small track-mounted geoprobe is sufficient to deliver the amendments. And of course, in the source zone, as depicted in the upper right here, the team used about 8 boreholes, and in each of those 8 boreholes, propagated fractures in 3 to 6 different zones. Of course, all of that targeted and optimized based on some of the visualization and the high-resolution membrane interface probe work and interpolated lithology and a number of other lines of evidence can all be used. In fact, one of the ways that they can look at the effectiveness of the permeability enhancement approach is to use tilt meters. And they used a concentric array of tilt meters around each borehole to map fractures, and we'll show you how they do that so we can get a sense of how well the permeability enhancement approach went. And in this case, each of the 8 boreholes placed in the source zone and each of those fractures, 3 to 6 fractures within those, received 140 gallons of a fracturing slurry, which includes about 550 pounds of microscale iron, 550 pounds of silica sand propagant. It also, they use a shear thinning guar product and a polymer crosslinker that helps to keep all of the slurry in suspension. As they emplace and hydraulically fracture the zones, then they must emplace that ZVI or that microscale iron in this case. And in the source zone, within those 8 boreholes, they actually were able to initiate a total of 39 fractures, emplacing almost 20,000 pounds of microscale ZVI and sand. And of course, those fracture initiation pressures that they use ranged from, in this case, in the source zone, between 80 and 240 pounds per square inch. And in fact, the contractor provides a look at pressure and pumping rates at each one of these locations, and then they can use those responses to understand where some of those fractures were initiated and propagated, in addition to the tilt meter information. So using pressure and pump rates along with the tilt meters to really do a good job of mapping out the propagation and the fracturing, and then the propagant or propagation of those mixtures. And the pump rate used was on the order of about 80 to 110 gallons per minute. So really using the high resolution site characterization, information to define a very small area, in particular driven by the lithology, or in this case the geology of the low permeability units, and then targeting that with a permeability enhanced approach that that not only enhances the contact necessary for an in situ remedy by fracturing the zone, but in placing the zero valent iron, which further enhances our reductive dechlorination and enhanced anaerobic bioremediation effort. So one of the nice things you get, as I mentioned, here are some of the tilt meter arrays placed in a concentric array around the geoprobe as it does its fracturing effort and delivers its amendments and places ZVI. And here are, of course, in each one of these locations, as I mentioned, they had, based on the high-resolution site characterization data and some of the visualization data, specific zones that they wanted to target for fracturing, but then they can also use the tilt meters and some modeling to estimate the orientation and propagation of those fractures at each one of these locations. So we can see the depth, the angle that they think the fracture was propagated at, and really get an understanding of how good the effort was to enhance the permeability within that source zone. And of course, you can put all of those together, in this case, you're looking at a transect, and this is an area that's actually down gradient. This was not done in the source area, but I'll talk about some of the down gradient. There's two areas down gradient where they tried very similar efforts of fracturing. But what's really nice here is you can look at that transect through a specific zone that you're targeting, put those together, and really see how you've done a good job of really hammering that zone with fracturing and emplacement of ZVI. So here we have the source zone tilt meter results. So this was the area done right around HMW 17D and within the source area of the parking lot. And there's a variety of ways that you can look at it, but here you can see those 8 individual borings which were used to fracture the formation and place the ZVI, but you also get an understanding of what the angles were and what the orientation of those fractures were in conjunction with each other. Here's a look at the surface, but also a look at the subsurface to make sure that that targeted zone at the right depth was properly fractured as well. And indeed, the tilt meters that were used indicated a pretty dense network of interconnected and overlapping fractures. And this was further confirmed by observations made in nearby boreholes, which I'll talk about in just a second. But you can see that all of the fractures had dip angles between 0 and 60 degrees, and that with 8 of those borings, they were able to encompass the source zone area, the low permeability units that they were after, with a pretty high degree of interconnected and overlapping fractures. And of course, we can check those results. In this case, checking the permeability enhancement and fracturing results was done by placing boreholes using a sonic drilling rig anywhere from 5 to 12 feet away from the initiation points of the fractures. And indeed, they were able to identify fractures with the sand and proppant observed, and even leak off of the darker iron into the sand lenses, nearby sand lenses. So in addition to the fracturing modeling and the enhancements done there, another line of evidence that you can use to really understand the efforts that were undertaken and the results of the permeability enhancement, the orientation and distance of some of those fractures, you can further use with conventional drilling techniques to find your in this case, microscale iron and sand propagant at various depths that you've targeted for fracturing, upwards of 5 to 15 feet away from where that fracture was initiated. So one of the ways we can look at the response of the system to our enhanced permeability efforts is to look at response in nearby monitoring wells, and we keep continue to show HMW17D as a good indicator of what's happening in the source area. I mentioned that there were two fracking events, the fracking event in the source area that took place in 2017 and the stuff that took place in 2019 is in two smaller down gradient units, which I'll show in a minute. But so we've got a little bit of data, a couple of years post the July 2017 permeability enhancements that took place. But one thing that we can show, of course, you're looking at, these are molar concentrations, micromoles per liter, early TCE responses, some breakdown products, and seeing a lot of DCE, perhaps an increase through 2012 to 2016 area where we're seeing a little bit more production of ethene, but not an overall downward trend. And then we see the fracturing event taking place in mid to late 2017, and the response where we really see an increased, we see very little of our main contaminant of TCE, and a big push to further that process along and actually go from DCE and vinyl chloride production and start to see a lot of production of ethene and fewer and fewer less production of DCE and vinyl chloride. And indeed, if we look in the lower right-hand corner, now we're looking at mass concentrations, but you see something very similar from the event in July of 17, where after the post-fracturing event, we see perhaps an initial kick up, but then a rapid drop of, in this case, the DCE product, and a real drop in vinyl chloride, and a nice uptick in the production of the full dechlorinated pathway to ethene. But we need to keep our eye on whether or not we have continued diffusion or matrix diffusion challenges with a tick up in the TCE concentration, which is what the biocirculation component of the enhanced remedy would deal with. Still looking in the treatment area now at HMW101D, but again, we can see following the July 17 event, response both in mass concentration and molar concentrations. We see a continued reduction, in this case, of TCE in red, whether we're looking at molar concentrations. So we're seeing our TCE concentrations doing a nice job of dropping, and our breakdown products responding accordingly. So initial rise in DCE, followed by a drop in DCE and perhaps a rise in vinyl chloride and ultimately ethene. And indeed, when we look at molar concentrations, like down here in the bottom right, for example, we can see this starts in August of 17, so just after some of those initial results, what that has done to the molar concentrations of the main contaminant TCE, but also the breakdown products. We're getting more production of vinyl chloride and getting to ethene more efficiently. Here we have a fairly similar situation, again, just a little bit down gradient in the treatment area, but at HMW 102D, and we see pretty similar responses to the 2017 fracking event with big drops in many of the products, and then after the event, an increase of ethene and a continued decrease of some of the other breakdown products, DCE and vinyl chloride, and also a continued low concentration or very low concentration of our main contaminant TCE. And we see that play out through a variety of efforts. So in this case, I've got data through 2020. So in the upper left, this is just after the injection in 2017, and we see indeed by 2018 or 2019, there's a little bit of an uptick for some of both the TCE concentration, but also look at the significant increase of those breakdown products, again, vinyl chloride DCE, and our biggest one, ethene, our biggest concentration. And we look at in molar concentrations, actually, it's even more significant. So in the upper right, just after the few months after the injection, we see an immediate decrease in our contaminant and DCE and vinyl chloride, and a bigger production of ethene, which we're trying to drive. And indeed, that plays out over a longer time frame in the bottom right-hand corner, where we're looking at just after the injection event in 2017 out through late 2019, but we'd see in mid to late, I guess it's late 2018, we start to see an uptick in some of the other breakdown products, including a big production of ethene, which is nice to see. But we also have a little bit of TCE, DCE, and vinyl chloride showing up as well. So something that they need to keep an eye on. And this is at RW1, again in the source treatment area. And we see a very similar response down gradient and in nearby monitoring wells from the 2017 event, with a big, I think it was on the order of 96% initial reduction in the TCE mass from the initial fracking events. We can see that we were almost on the order of 25 micrograms per liter, down to very, very low concentrations below 5. And if we can continue to keep that there, that's a goal. 5 micrograms per liter, for instance, for TCE is the maximum contaminant level, and oftentimes the number they're shooting for in groundwater cleanups. So here we have a big reduction, but we're starting to see a little bit of an uptick within a few months, possibly some continued diffusion happening in those newly fractured zones. So it's a double-edged sword in that we're immediately reducing contaminants, but we're also opening up some zones where we may get access to contaminants quicker than the diffusion rates, which they are typically limited by. And indeed, we see after the fracturing event at RW1 a big drop in DCE, and a nice drop in our TCE, followed by several months later nice upticks in our breakdown products, specifically if we can get that vinyl chloride in purple and the DCE in green to make it all the way to the ethene, which we are looking for down here in the bottom right. So this was upper right is immediately after the injections. We see a good decrease in vinyl chloride and DCE, and a big jump up in ethene, which we really want to see. And over a longer time frame, from just after the ejection or the fracturing event in 2017 out through towards the end of 2019, we see sustained production of ethene, but we also see a little bit of an uptick in some of those other products, which means that's the EAB is working, the bioremediation is working, and we are getting breakdown of those products which were previously challenging in some of those areas. Now this is down gradient of the source area, but similar to what happens in wells right in the source area. Similar situation happened post-fracturing events in the source area down gradient as well, where we see we already had significant increases or decreases in mass concentrations due to the ongoing efforts. We see the 2017 permeability enhancement event followed by a small uptick in some of the contaminants that we're trying to liberate and bioremediate at the same time. So that's actually a good thing as well. We see post-fracturing a small uptick in a couple of the breakdown products, which we are trying to stimulate that process. So looks good in the source area as well as down gradient, and it's just a matter of monitoring that process and making sure we are continuing at a good rate. And because of the promising data that was shown and the costs really associated with taking a very small and targeted action in the source zone with the permeability enhancement and emplacement of the ZVI, the team looked at opportunities to do that at 2 locations down gradient. Just down gradient from the source area in the parking lot, you find 2 wells, HMW 19D, which is closer to the source area, and then a little further down gradient, HMW 14S. And each of those in 2019 had a fracturing event similar to the fracturing events that we saw take place in the source zone in 2017. And indeed, they were able to produce a lot of the same types of maps. So a good understanding of the placement. I think there were 30 borings used in these two zones. Remember, the source zone received about 8. It was a fairly small area. There's about 30 borings between the 14S and HMW 19D areas. But again, you can see from the depictions and the modeling from the tilt meters that they've done a good job of really fracturing at the depths and within those zones that they specifically hope to enhance the permeability at. And the process was the same as used in the source area. So you end up with very similar looks of, in this case, nice productions from geotactical of what the fracturing looks like. But because this work was done in 2019, there isn't a lot of data to say what the permeability enhancement looks like at these locations, but suffice to say that it is promising, as is 2 years or 3 years worth of data coming out of the permeability enhancements that took place in the source zone. So the permeability enhancement effort at Bountiful OU1 has certainly been, if not driven by high-resolution site characterization, certainly aided by it. The delineation of the source zone, remember that 400 some odd square foot area that was depicted from the MIP, was really critical to targeting a small targeted action, a remedy implementation at a scale and cost that the project could actually afford. So the team felt good at one thing that the high resolution site characterization tools offer the team is the ability to, if they are going to be aggressive in areas, to keep that effort targeted on very small zones typically associated with the low permeability units. And in fact, the fracturing and placement was shown to be effective at distributing the zero valent iron and low contacting contaminant and low permeability areas, both in the source zone and, as I mentioned, just down gradient. I think 19S is just over here, and 14S is over here, and 19D is right here in the corner of this picture. 14S is just off the map. But we're looking at sustained contaminant reduction to date, so looking at some of those molar concentrations and the reduction in the mass, the good production of ethene that we're seeing, along with the sustained and downward trends in DCE, vinyl chloride, and ultimately our TCE mass. All those things mean that at this time, the planned biorecirculation, which included some injections and then recirculation of that water across the zone, so recirculating the water from just up gradient here, probably, and then pumping it back up through these source zones is the next step. However, the fracturing has done such a nice job and the data looks so promising that to date the biorecirculation is not necessary, but recent data has shown a little bit of an uptick in a couple of concentrations that we need to keep an eye on that may be diffusion limited or diffusion impacts that could be addressed with the biorecirculation if necessary. And lastly, I would say one of the great things about the Bountiful Operable Unit 1 site and its history has been sort of the fact that the team, the EPA team, their contractors, CDM Smith, the state of Utah, all have been amenable and eager to use and employ triad techniques, high resolution site characterization, and even adaptive management as they move into applying the remedy. And so what I mean by that is that the team has done a really great job of compartmentalizing the site, right? So determining where the source areas are, where the plume, diffuse plumes are, and where the plume cores might be. And in this case, going in with some high resolution techniques to really hone in on some hotspots, for example. So if you look over at, like in the source area here for the in situ bioremediation, trying to expedite that process. How did they use some of the high resolution and triad techniques? Well, they used membrane interface probe, step-out sampling, targeted treatment. Remember, they use the biobarriers and other things to do their injections of lactate, and then of course coming back in later on with the hydraulic permeability enhancement and placement of zero-valent iron in that source area. At the same time, they've monitored and really done a nice job of mapping out the plume cores in this case, and then targeting those plume cores using high-resolution site characterization tools and biobarriers and a series of injections as well to target that. In the down gradient plume, they're using the hydraulic profiling tool and high-resolution vertical groundwater sampling, and that's going to help them deal with identifying those plume pathways, those down gradient plume pathways, and target monitoring well placement, which can be really important for ultimately trying to determine that you've achieved restoration in the aquifer. And then in the down gradient hotspots, of course, they're using the membrane interface probe hydraulic profiling tool, so the new MIHPT, and delineating those zones down in 14S and 19D and some of those later zones that I mentioned, and dealing and using the same strategy of hydraulically fracturing and in placing zero-valent iron using a sand to accelerate the plume cleanup. So finally using an adaptive remedy implementation, looking at the data as it comes in and looking for opportunities to optimize and target specific zones to expedite the overall cleanup of the aquifer. So thanks to the team. I want to thank everyone I mentioned in the first slide again for all their great work and help in putting this presentation together.